Hello everyone, this is Nipa Patel from the Math Masters in Nashua, New Hampshire. This is the first video of the series of NCERT Class 12 Math, and today we are going to start Chapter 1 Relations and Functions Exercise 1.1. Please like the video and subscribe to get the notifications of new and upcoming videos. Let's get into it. Exercise 1.1, Question 1. Determine whether each of the following relations are reflexive, symmetric, and transitive. Relation R in set A equals 1, 2, 3, and so on till 14, defined as R equals x comma y, where 3x minus y is equal to 0. Now let's try to understand what this set R is. So you are given a relation between x and y such a way that 3x minus y is equal to 0. Now you are given this linear equation, so I can solve for y. So y is equal to what? 3x. So if you are taking your element from this set A, because this relation R is in set A, so this relation is from A to A because that relation is in set A. So if you are taking one number from A, so that means if you take x is equal to 1, then y is going to be what? You are given this relation y equals 3x. So 3 times 1, y is going to be 3. If you take x is equal to 2, then y is going to become 6. If x is equal to 3, then y is going to be 3 times 3, so 9. When x is 4, y is going to be 4 times 3, to 12. X equals 5, then y is going to be 5 times 3, so 15. Let's stop here and think for a while. So you are given set A where your numbers are starting from 1 and ending at 14. Your all x belongs to this set A and all your y's also from this set A. Now if you look at this, x equals 5, is it in set A? Oh yeah, it is. But y equals 15, y must belong to set A as well. Y equals 15, we cannot find that 15 in this set A. So this number pair we cannot take in our set R. Why? Because the relation that you are given, by that relation, if you take x equals y, there must be y that is equal to 15, and our set A does not have that element in it. So in short, your set R is made up of these elements: 1 comma 3, then 2 comma 6, then 3 comma 9, and 4 comma 12. These are the elements in your set R. Now we need to determine whether this relation is reflexive, symmetric, or transitive. Now let's start with reflexive. Now what is the definition of a reflexive relation? It is that it is going to be reflexive if A comma A belongs to R for every A belongs to A. So look here, if we take 1 equals A, then 1 comma 1, that must be in relation R. We don't have that. So this relation is not reflexive. So R is not reflexive, and the reason being because 1 comma 1 does not belong to R. We had to determine whether that relation was reflexive or not, and reflexive definition is what? That A comma A must belong to R, where your A belongs to A. Now if you take if you take A equals 1, then 1 comma 1. If you take 2 equals A, then 2 comma 2. If you take 3 equals A, then 3 comma 3. This kind of elements must be there in your relation R to be reflexive, but none of them are here. So that relation that we are given is not reflexive. Now we are going to check for symmetric. Now the definition of symmetric is what? That if you are given that, let me write this way, if A comma B belongs to R, then B comma A must also belongs to R. Right? Like if you have 1 comma 3 in R, that means 3 comma 1 must also be in R. But our y is always 3 times bigger than x. So 3 comma 1 will never be in our relation R. And see, we can see here 1 comma 3 is here, but 3 comma 1 is not here. So that means it is not symmetric either. Right? So we are going to write R is not symmetric, and reason being because 1 comma 3 belongs to R, but 3 comma 1 does not belong to R. Okay, so we checked for reflexive, it is not reflexive. We checked for symmetric, it is not symmetric either. Now it's turn that we need to check for transitive. Now definition of transitive is what? That if A comma B belongs to R and B comma C belongs to R, that means A comma C must also belong to R. Okay, that means like this, if 1 comma 3 belongs to R and 3 comma 9 belongs to R, then 1 comma 9 also belongs to R. Right? See here, A comma B belongs to R. So we can take this 1 comma 3. So 1 comma 3 belongs to R, okay, and B comma C belongs to R. So something which starts with the end number of this. So that was 3 comma 9. So 3 comma 9 also belongs to R. Okay, so we have that kind of element in our relation R, that 1 comma 3 is in R, 3 comma 9 is R, but then A comma C must also belong to R. So A was 1 and C was 9. So 1 comma 9. Do we have 1 comma 9 here? No, we don't. So this is not transitive either. So we are going to write R is not transitive, and the reason being because 1 comma 3 belongs to R, 3 comma 9 belongs to R, but 1 comma 9 does not belong to R. Now second part, again you need to check for reflexive, symmetric or transitive relation, and in this question you are given relation R in set n, natural numbers. What is natural number set? That it starts from 1, 2, 3 and keeps on going. So natural number set is going to start at 1 and all the whole numbers, and that relation defines as x comma y, where y is equal to x plus 5. So y is always 5 bigger than x, and one more condition you are given, that your x must be less than 4. So your x cannot be 4, but it must be less than 4. Now your x also belongs to this set, natural number set n. So your x or possible x are what? 1, 2 or 3. Why? Because your x must be less than 4 and less than 4. So if you have like 4 somewhere here and then keeps on going, then your x cannot be 4, it cannot be 5, it must be less than 4. So only 3 possibilities that we have for x values are 1, 2 and 3. Now from this given definition, we can decide what the y value is going to be. So when x is equal to 1, your y must be what? See, y equals x plus 5. So x means 1, 1 plus 5, so x is going to be 6. When your x is equal to 2, your y must be 7. And when your x is equal to 3, your y must be 8. So what relation we got? That R is equal to 1 comma 6, because we got this element. So 1 comma 6, then 2 comma 7 and one more 3 comma 8. Okay, so these are all the elements in that relation R. And now we need to decide whether this relation is reflexive, symmetric or transitive. Let's start with reflexive. Okay, so definition of reflexive relation says what? That if A comma A belongs to R for every A belongs to A, then that relation is reflexive. So can we see 1 comma 1 here? Can we see 2 comma 2 here? Can we see 3 comma 3 here? No. So this is not reflexive. So we are going to write R is not reflexive. And the reason is because 1 comma 1 does not belong to R. Because reflexive means what? Like 1 comma 1, 2 comma 2, 3 comma 3, those kind of elements must be there in that set. We got none of those. So R is not reflexive. Now let's check for symmetric. Okay, now definition of being a symmetric relation is that if you have A comma B in your set R, then there must be B comma A also in that set R. Okay, so look here, you got 1 comma 6 here. That means if 1 comma 6 in R, that means 6 comma 1. See, AB, BA. So if 1 6 is in R, that means 6 1 must also be in R, but we don't have any, right? So we are going to write, so R is not symmetric, and the reason is that because 1 6 is in that R, but 6 1 does not belong to R. Now let's check for transitive. Now the transitive definition says what? That if you have AB which belongs to R and if you have BC which also belongs to R, then there must be AC in that set R to be a transitive relation. Now let's look here, 1 comma 6. Do we have 1 comma 6 here? Yeah, because we are taking that. Now if 1 comma 6 is R, if 1 comma 6 is in R, that means 6 comma something, right? See, AB then BC. So 1 6 then 6 something, no, we don't have any. 2 7 then 7 something, no. 3 8 and then 8 something, no. We got none of those two set of numbers that, two set of relations that you can have in that relation, two set of elements that you can have in that relation. We don't have any, so this is not transitive either, because if we have these two, then we are going to check for this, but we got none of this, so it's not transitive at all. So R is not transitive because there is no coordinate, like if that is no coordinate pair present with B in common. See, do we have any B in common? See, you got 1 comma 6, we don't have any 6 comma something. 2 comma 7 we have, so 7 comma something we don't have. So we don't have that B in common in any of those coordinate pairs. So R is not transitive. So reason is that because there is no coordinate pair present with B in common. Number 3, relation R in the set A equals 1, 2, 3, 4, 5, 6 as R equals x comma y, where y is divisible by x. Let's try to see which kind of elements are going to be there in this set R. Now y must be divisible by x. So that means we can take 1 with any number because any number is divisible by 1. So I can write 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6. Why? Because the condition was y is divisible by x. 1 is divisible by 1, 2 is divisible by 1, 3 is divisible by 1, 4 is divisible by 1, and so on. So we can write down all these elements. Now try to use x equals 2. So if x is 2, then which number is divisible by 2? So it must be an even number. So 2 is divisible by 2. Then 4 is divisible by 2. Then 6 is divisible by 2. So we will be able to write these three elements with 2 as our first element. So 2 is divisible by 2, 4 is divisible by 2, 6 is divisible by 2. We cannot write 2 comma 1 because 1 is not divisible by 2. So cannot write 2 1, cannot write 2 3 because 3 is not going to be divisible by 2. So that's why I wrote just this 3. Now if we use x equals 3, then which number is divisible by 3? So 3 comma 3 and 3 comma 6, because 3 is divisible by 3, 6 is divisible by 3. Now if we start with 4 in the front, then which numbers are divisible by 4? Okay, so just 4 in this set A. So 4 comma 4 is in the relation R. Same way 5 comma 5 is in the relation R, and 6 comma 6. I cannot think any other than this. Why? Because 4 is divisible by 4. There is no other number which is divisible by 4, and there is no other number than 5 which is divisible by 5, and just 6 is divisible by 6 from this number. So I think this is the whole set R with all the possible coordinate pairs. Now we need to check whether this relation is reflexive, symmetric, or transitive. So let's start with reflexive. Now the definition of reflexive relation is what? That if A comma A belongs to R for every A belongs to A. So if 1 belongs, see, 1 belongs to A, so 1 comma 1 must be there. Yeah, it is there. Then 2 belongs to A, so that means 2 comma 2 must be there in here. 2 comma 2, yeah, it is there. Then 3 is there in A, so 3 comma 3 must be in our relation R, which we already have. See, 3 comma 3. Now 4 is in A, so 4 comma 4 must be there in our relation. 4 comma 4, yes, it's there. Same way 5 comma 5 is also there, 6 comma 6 is also there. So we got for every A comma A belongs to R. So looks like this relation is reflexive. So R is reflexive. Reason is because of this definition, because A comma A belongs to R for every A belongs to R. Okay. Now we are going to check for symmetric. Now the definition of symmetric is what? That if you have A comma B belongs to R, then you must have B comma A belongs to R. That's the definition of being a symmetric relation. So if you have, let's say, 1 comma 2 in relation R, then you must have 2 comma 1 also in that relation. Now in this case it is what? Y is divisible by X, that kind of relation. So 1 comma 2, yes, 2 is divisible by 1, so it is here. But as soon as it is 2 comma 1, then it is going to be what? That 1 is divisible by 2, which is not correct. 1 is not divisible by 2. So since this coordinate pair is not present, it's not symmetric, right? So we are going to show that 1 comma 2 belongs to R, but 2 comma 1 does not belong to R. So R is not symmetric. Now we need to show whether it's transitive or not. Now the definition for transitive is what? That if you have A comma B in R and B comma C in R, there must be A comma C in R. See, both have that B in common. So if you have A comma B, that element in R, and if you have B comma C in R, there must exist A comma C in R to be a transitive relation. So for this, the condition was what? That y is divisible by x. That means this b must be divisible by a and this c must be divisible by b. So if we think that in this relation a comma b is in R, that means from that condition b is divisible by a, right? We were given what? Y is divisible by x. That means b must be divisible by a, and since b is divisible by a means, let me keep the same color. So since b is divisible by a, that means I can say b is a multiple of a. So I can write like this, that b must be some number times a, because b is multiple of a, right? Why? Because b is divisible by a. Now for b comma c, that condition is going to be what? That c is divisible by b. And if c is divisible by b means c is a multiple of b. So for this we can take some other constant. So that let's make it n. So c must be equal to n times b. Why? Because c is a multiple of b. So b times some number must be c. Now if b is equal to ma, if c is equal to nb, and here we said what? That if these things are there, then there must be a comma c in R. Now a comma c means what? C is divisible by a. That means c must be a multiple of a. So if I try to write this one more time, c equals n times b, but there is no b here, so I'm going to try to plug in this value over there. So b is equal to ma, so n is equal to, sorry, c is equal to n times ma, so this is going to be what? M n a. So actually we got what? Yeah, c is going to be multiple of a. Why? Because n and m are some constant, and looks like c is equal to some number times a. So that means this implies that c is a multiple of a, and that implies that c is divisible by a. So yeah, looks like it is going to be a transitive relation after all. So we are going to say what? Yes, it is transitive. Or let me write the same way. Yes, R is transitive relation as well. Now part 4 of this question, you are given that relation R in the set Z of all integers defined as R equals x comma y, where x minus y is an integer. So let's check this for again all of these three: reflexive, symmetric and transitive. Let's start with reflexive. Now the definition of reflexive is what? That if you have a comma a in R for every a belongs to a, then it is a reflexive relation. Now let's check here. Let's say that x is your a. That means x comma x belongs to R. To check that, think this: x minus y is an integer. That means x minus x must be an integer. So x minus x is what? 0. Of course 0 is an integer, so it's going to belong to R, right? Why? Because 0 is an integer, so x comma x is going to belong to R. Because to belong to R, just this condition must be true, that x minus y is an integer. Here x and y, they both are same, so x comma x, because it is reflexive. So if x minus x, if you are going to try to do at any value of x, even negative 1 minus negative 1, you are going to end up getting again 0. 0 minus 0, 0. 3 minus 3, 0. So for every a which belongs to a, this a comma a, this x comma x will always going to give you the difference of x and x is always going to give you 0, and 0 is a member of integer set Z. So x comma x belongs to R for every x which is in A, for every A which is in A. So this relation, so the relation is reflexive. So the relation is reflexive. Now let's check for symmetric. Now the definition of symmetric says what? That if you have some a comma b belong to R, then you must have the reverse of it. The b comma a must also be there in that set R. Okay, so if we say that xy belongs to R, let's say that xy belongs to R. Now, if xy belongs to R, that means x minus y is an integer, right? So this implies that x minus y is an integer. If x minus y is an integer, I can say that negative of y minus x, this is the same thing, right? See, x minus y or negative of y minus x. If you distribute this negative sign in here, you are going to get negative y and then negative times negative x, so x minus y. So this is actually exactly the same. So if x minus y is an integer, then negative of y minus x is also an integer, right? Because they both are actually the same things. Now, if negative of y minus x is an integer, that means y minus x is also an integer, right? Why? Our integer set looks like this, lot of things, and let's say negative 3, negative 2, negative 1, 0, 1, 2, 3, and then keeps on going until infinity. So if you have negative 3 in this set, you have 3 in this set. If you have 1 in this set, then you have negative 1 in this set. So if you have negative of y minus x as integer, then of course y minus x is also going to be an integer set, right? It's also going to be in there in that set Z. So y minus x is an integer, and since y minus x is an integer, that means we can say that y comma x, that implies that y comma x belongs to R, and that means we had to get to this, that b comma a belongs to R. So our y was actually b. See, we took x for a, y for b, so actually b comma a belongs to R. That's what we wanted. So for every ab belongs to R, we will have ba also in that set. So actually this relation is symmetric. So yes, it is symmetric. Yes, it is a symmetric relation. Now we need to check for transitive. Now the definition of transitive says what? That if you have AB belongs to R and BC belongs to R, there must be AC belong to R. Why? See, B is in common in both of them. So if you have some element AB in R and some element B comma C in R, then you must have AC in R. Now, if I say that XY instead of this, let's say XY instead of this. So let XY belong to R and let Y comma Z belong to R. So I am taking A equals X, B equals Y, and C equals Z. See, B equals Y, we already took that. So we are taking XY belongs to R, and from that condition, if XY belong to R, then X minus Y is an integer. So if we have XY in R, then there, what can we say? That X minus Y is an integer. And what did we say? That we have Y, let's say that we have Y comma Z also in R. That means Y minus Z is an integer, right? Because that's what the condition is to be in that set. And if you already have XY in relation R, XY in set R, then X minus Y is an integer. And if you already have Y comma Z in R, that means Y minus Z is an integer. And if I try to add both of this, let's add X minus Y and let's add this Y minus Z. So add equation 1 and 2 and you are going to get what? X minus Y plus Y minus Z. And you are going to get Y and Y is going, negative Y and Y is going to cancel out. So X minus Z. Now if this was integer, then yeah, addition of that is also an integer, and that's going to be an integer, right? X minus z is an integer, and if x minus z is an integer, then x comma z belongs to R. But x was a, so a, and z was c, so ac belongs to R, and c, we proved it, that if you have ab in R, if you have bc in R, then ac is also going to be in R. So yes, it is transitive. Now, fifth part in that question, you are given relation R in the set A of human beings in a town at a particular time given by A. R equals x comma y, where x and y work at the same place. And we need to check this for reflexive, symmetric, and transitive relation. So first, your set A is what? That all the human beings, that means all x, where x is a set of all human beings in a town at some time. Okay, now let's check for reflexive. Now, to be a reflexive relation, what we know, that a comma a must belong to R for every a belongs to a. Now, if x is in a, and the condition is what? X and y work at the same place. So that means x comma x must belong to R if it is a reflexive relation. So if x is in A, that means x comma x must be in R. And what is the condition? That x and x must work at the same place, because we got x comma x, then x and x must work at the same place, of course. So the reason why x comma x belongs to R, because x and x work at the same place, because every entity is related to itself. So x is going to be related to itself. Why? Because x and x, that person and that person itself, that person is going to work at the same place, of course. So x comma x is also going to belong to R. So yes, it is reflexive. Yes, it is reflexive, because x comma x, x and x is going to work at the same place. If you pick y, then y and y is going to work at the same place. If you pick some c, then c and c is going to work at the same place. So yeah, it is going to be reflexive. Now let's check for symmetric. Now the definition of being a symmetric relation is what? That if you have some AB belong to R, then you must have B comma A belong to R. Now if you have A comma B belong to R, that means this implies what? That A and B both work at same place. If we take A as x, B as y, then x and y both work at the same place. So if x and y work at the both, if x and y both work at the same place, means y and x also work at the same place, right? If A and B both work at same place, means B and A also work at the same place. So B comma A, this means B comma A belongs to R. So we started with A comma B belongs to R, and that means A and B was working at the same place. And if A and B work at the same place, means B and A work at the same place, and that means B comma A belongs to R. So yes, it is symmetric relation. Now we need to check for transitive. Now the definition of transitive relation is what? That if you have A comma B belong to R and if you have B comma C belong to R, then you must have A comma C belong to R. Now if you have A comma B belongs to R, this means what? That A and B work at the same place. Now if you have B comma C belongs to R, that means what? That B and C work at the same place. Now what information you have? A and B work at the same place and B and C work at the same place. That means, yeah, of course A and C work at the same place. So this implies that A and C work at the same place, and since they work at the same place, we can say A comma C belongs to R, right? So it is transitive as well. So yes, it is transitive. Now part B in question. In part 5, you are given relation R in set A of human beings in a town at a particular time given by R equals x comma y, where x and y live in the same locality. So we need to check for reflexive, symmetric and transitive. So let's start with reflexive. Now the definition of reflexive relation is what? That you must have A comma A belongs to R for every A belongs to A. So let x comma x belongs to R. Now if x comma x belongs to R, and in this case you are given what? That x and y live in the same locality. So if x and x belongs to R, let's see that makes sense or not. So this implies that x and x live in the same locality. Of course that makes sense, because that person and that person itself, it's going to of course live in the same locality, right? So yeah, every human being is related to himself. So yeah, makes sense. So yeah, of course x comma x is going to belong to R. X comma x is going to belong to R. So yes, it is reflexive. Now let's check for symmetric. Now the definition says what? That if you have A comma B belongs to R, then you must have B comma A belongs to R. Now in here, what condition you are given? That x and y live in the same locality. So let x comma y belongs to R, and that implies what? That x and y live in the same locality. And if x and y live in the same locality, I can say that y and x live in the same locality. Right? Of course, if x and y live in the same locality, then y and x live in the same locality. And that means y comma x belongs to R. And that means B comma A belongs to R. That's what we were supposed to prove, and we got that. Why? Because if x and y live in the same locality, then y and x live in the same locality. That means y comma x is in R, and y was B, x was A, so B comma A is also in R. So yes, it is symmetric relation. Now we are going to check for transitive. Now for transitive, the condition is what? That if you have AB belongs to R and you have BC belongs to R, then you must have A comma C belongs to R. Now we are going to do what? Let X comma Y belong to R and Y comma Z belong to R. We took A equals X, we took B equals Y, we took B equals Y, of course, that's what I just said, and we took C equals Z, C equals Z. So Y comma Z also belongs to R, right? Now what was the condition? If XY belongs to R, that implies what? X and Y live in the same locality. And if Y, Z is in R, that implies that Y and Z lives in the same locality. So if X and Y live in the same locality and Y and Z live in the same locality, means X and Z live in the same locality, right? So this implies that X and Z live in the same locality, and that means X comma Z belongs to R. That means A comma C belongs to R, because we took X instead of A and we took Z instead of C. So A comma C belongs to R. That's what we were supposed to prove, and we got it. So yes, it is transitive as well. So now in part C, we are given R equals X comma Y, where X is exactly 7 centimeter taller than Y. And we need to check whether that is reflexive, symmetric or transitive. So let's start with reflexive. Now definition of reflexive is what? That if A comma A belongs to R, for every A belongs to A, then it is reflexive relation. Now let X comma X belong to R. Now if we assume that X comma X belong to R, that means we are saying what? Because see, what is this condition? That X is exactly 7 centimeter taller than Y. So if X comma X is in R, that means we are saying that X is exactly 7 centimeter taller than X. Is that possible? That X is exactly 7 centimeter taller than itself. So it's not going to be possible. So it's not true. It's not true. That means X comma X does not belong to R, and that means A comma A does not belong to R, and that means so not reflexive. So this relation is not reflexive. Why? Because X can not be 7 centimeter taller than itself, right? Okay, so not reflexive. Now we are going to check for symmetric. Now definition of symmetric is what? That if you have AB belongs to R, then you must have BA belong to R. Now here again let X comma Y belong to R. Now if we say that X comma Y belong to R, that means, sorry, let me write this way. So this means what? That X is exactly 7 centimeter taller than Y. That's what we were given, right? This condition. X is exactly 7 centimeter taller than Y. So if x comma y is in R, that means x is exactly 7 centimeter taller than y. Now can we write this in converse way, like in other way around, that y is 7 centimeter taller than x? What information you got? That x is exactly 7 centimeter taller than y. That implies that y is exactly 7 centimeter taller than x. No, does not make sense. So this does not imply that y is exactly 7 centimeter taller than x, because it's not going to be true. This is not true. That means y comma x does not belong to R, and that means b comma a does not belong to R, and that means it is not symmetric. So not symmetric. So this relation is not symmetric either. Now we are going to check for transitive. Now the definition of transitive says what? That if you have a comma b belongs to R, if you have b comma c belongs to R, then you must have a comma c belongs to R. So let x comma y belongs to R, let y comma z belongs to R, and we will see that do we have x comma z belong to R or not. So if we have x comma y belongs to R, that means x is exactly 7 centimeter taller than y, and if y comma z belongs to R, that means y is exactly 7 centimeter taller than z. Now if x is 7 centimeter taller than y and y is 7 centimeter taller than z, can I say that x is 7 centimeter taller than z? No, because x is actually double than 7. So x is 14 centimeter taller than z. So that does not imply that x is 7 centimeter taller than z. Or in other words, I can say this does not imply that x is 7 centimeter, exactly 7 centimeter. Again, they are saying what? It must be exactly 7 centimeter. So this does not imply that x is exactly 7 centimeter taller than z. That means x comma z does not belong to R, and that means a comma c does not belong to R. So it is not, not transitive. Now part D of that fifth part, R equals x comma y, where x is wife of y. So again we need to check for reflexive, symmetric and transitive. So let's start with reflexive. To be a reflexive relation, you must have what? A comma A belongs to R for every A belongs to A. Now let x comma x belongs to R, and what is the condition? X is wife of y. So if x and x belongs to R, that implies that x is wife of x. It's not going to happen. So we are going to write it's not true. So it is not reflexive. Now we are going to check for symmetric. Now definition of symmetric says what? That if you have a comma b in R, you must have b comma a in R. So let x comma y belongs to R. Now if x comma y belongs to R, that means from this condition x is wife of y. Yeah, if x is wife of y, if that is given, yeah, it is believable. They both are different person and it is possible that If X is a girl and she is a wife of Y, then yeah, X is wife of Y. But does that imply that Y is wife of X? Nope. That does not imply that Y is wife of X. It's not true. So Y comma X does not belong to R, and that means B comma A does not belong to R, and that means it is not symmetric. That relation is not symmetric. Let's check for transitive. Now definition for transitive is what? That if you have AB belongs to R and you have BC belongs to R, then you will have AC belongs to R. Okay, so let XY belongs to R and YZ belongs to R, and then we will see that do we get XZ belongs to R or not. Sorry, XZ belongs to R or not. Okay, so let's first see that whether this is going to be true or not. So if X comma Y belongs to R, then we are saying that X is wife of Y. Yeah, that can be true, yes. And then if Y comma Z belongs to R, that means we are saying that now now we are saying Y is wife of Z. So if X is wife of Y, this does not make sense at all. Then Y is a husband. How can Y is the wife of Z? So not true. So if this is not true, then we cannot go forward. So even this part is not true. So it's not going to be. So even Y comma Z does not belong to R. So of course, so A comma C will never belong to R. And so it is not transitive. Okay, now E part of this fifth part of question 1. You are given R equals X comma Y, where X is father of Y. So we need to check again that relation is reflexive, symmetric or transitive. Let's start with reflexive. Now definition of reflexive says what? That A comma A belongs to R for every A belongs to A. So let's check. Let X comma X belong to R. Now if X comma X belong to R, that means what? That X, which condition we are given? X is father of Y. So in this case, X comma X, we are saying that X is father of X. Oh, not true, right? How can X be father of X? So it's not true. And so we can say, so it is not reflexive. Okay, now we are going to check for symmetric. Now symmetric relation, symmetric definition says what? That if you have some element A comma B in R, then you must have B comma A in R. So let X comma Y belongs to R. And if X comma Y belongs to R, that means from this condition, X is father of Y. Now if X is father of Y, does that imply that Y is father of X? No, of course not. If X is father of Y, that does not imply that Y is father of X. So Y comma X does not belong to R. That means B comma A does not belong to R, and that means it is not symmetric. Now we are going to check for transitive. Now definition of transitive says what? That if you have A comma B belongs to R and B comma C belongs to R, then you must have A comma C belongs to R. Okay, what does it say? That if you have A comma B belongs to R And if you have B comma C belongs to R, then you must have A comma C belongs to R. If that happens, then that relation is transitive. So let X comma Y belongs to R and Y comma Z belongs to R. So I am taking A equals X, B equals Y, see, B equals Y, and C equals Z. Now, if this is in relation R, that means it implies from this condition that X is father of Y, I can write that down. So if X comma Y belongs to R, that means X is father of Y. And if Y comma Z belongs to R, that means I can say Y is father of Z. Is this possible? If you have X comma Y in R, then yeah, X is father of Y. Okay, let's say Y is son, X is father of his, and Y comma Z belongs to R, and it says Y is father of Z. So it is possible that X was a grandparent, Y was a dad, and Z was a son of that dad. So yeah, it is going to be possible. But does this means that X is father of Z? Does that imply that X is father of Z? No, it does not, because X is grandfather of Z, right? So that means X comma Z does not belong to R, and that means A comma C does not belong to R. So it is not transitive. Okay, so that's it for today. See you all soon in the next video. Thank you.